Okay, welcome back. We're looking at some of the questions from section 16.6. So we're not given any diagram, so hopefully the situation will be pretty simple. We're to find the length of an arc of a circle of radius 6 centimeters. Okay, so let's just draw that. I'm not going to use exactly 6 centimeters, it doesn't matter, I'll just call that 6 centimeters. Stand at an angle of 2 radians. Now we do want to get an idea of what does 2 radians look like. So 2 radians is out here somewhere. So we're finding that length there. Okay, well the formula L equals R theta means you have 2 for theta and you have 6 for radius, and it's that simple. Okay, so the length equals 12 centimeters. Because 1 radian gives us 6 centimeters and another radian gives us another 6 centimeters. So 12 centimeters. So hard to say really. I mean, there wasn't a whole lot of challenge there. Moving on to question 2. So a piece of cake is in the shape of a sector, great, of a circle with center knot and radius is 12 centimeters. So straight away, before I even read on, I can see I can work out the number of radians by dividing 18 by 12. Find this angle in radians. Well, that's the convenient thing to do. So in radians, again, if you have to justify it, you're working off this formula here. The definition of theta is L over R, or the length of arc is equal to R theta, which defines what a radian is. Okay, so theta equals length over R, and that's in radians. Radians is the default angle. We don't really say anything. We don't even give it a unit. So if we specify degrees, we don't specify anything special here. So you have 18 over 12. Okay, now that will reduce. 6 will go into both of them. Just to be sure, I say there's no need for any heroics in mental maths when you're doing higher level maths. Just let the calculator tell you that that's 3 over 2. Okay, so that's the number of radians. It's 3 over 2. That's the answer. And then in degrees to the nearest degree. So what I'll do is I'll take the answer I already have and I'll convert it to degrees. So my conversion. And it's quite okay to not even remember which of these it is. Is it pi over 180 or is it 180 over pi? Because logic will tell you that you want the pi on top. You're moving into so you've 3 over 2. What am I doing? In radians it's 3 over 2. And in degrees, so no, I'm wrong. It has to be multiplied by 180 over pi. But I'm surprised the pi is at the bottom. What's going on here? Yeah, you just do the calculation and let the pi cancel out. So it's 180 over pi. So, and because they want it in degrees, you just let that pi go in. They're not asking it in terms of pi, because you just don't give degree answers generally in terms of pi. So we do that calculation out on the calculator. So we can turn it into a single fraction by going 3 by 180. Yes, of course, there's loads of cancellation was going on there, but if I have to pick up the calculator anyway, there's no. It's not a particular advantage to nudge it forward at all. So that comes out to be 85.9. You check to the nearest degree, so that's correct, and then 86 degrees is correct to the nearest degree. Okay. We move on to question 3. So this time we have to find the area of a sector of radius 18. So let's mark this up, 210 degrees. So it's called a major sector. because it's more than 180 degrees, so it's a major sector, but that's okay. And it's 210 degrees here, and this is 18 centimeters. Okay, so in this case we'll go to the formula, because when it's in degrees it's kind of messier. In terms of the area is pi r squared, the angle over 360 degrees. Pi, so the area equals pi r squared, the angle over 360 degrees. Okay, in this case pi times 18 squared, the angle 210 over 360. And we haven't time for mental maths right now, we're just going to go straight to the calculator. Okay, and it doesn't say in terms of pi, so I'm going to let the pi go in as well. So basically we have a fraction bar somewhere, so I'll kick off with just a fraction bar. This can all go upstairs. So I'm going to go 18 squared multiplied by pi. Your multiplication symbol is your friend, okay? So sometimes you can get away with leaving it out, but it's hardly worthwhile figuring out what those times are. It's easier just to just fill in the multiplication sign. It only takes a split second. So the calculation goes in the calculator like so, and we get, of course it's going to say 189 pi, and I'm going to have to kind of overrule that and say, could you give it to me in digital, in a digitally expanded form, which it's doing there now. So the area equals, we just want to be very careful about our units here now coming up. So 983.7, they probably went, now we just check for what kind of precision they're looking for. Find the area. It doesn't say, so let's leave it. We'll give them 5 figures. There's no particular reason why we shouldn't, but the units are quite important there, to give it centimeters squared. Okay, we move on to question 4. So we're going to find the area of a sector of a circle of radius length 12 if the angle at the center of the sector is 2 pi over 3. Now pi over 3 is 60, so that's 120 degrees. And you do want to try to represent your work always based on the in a standard angle position. Okay, so it's just no harm in representing it somewhat realistically by getting the idea of obtuse, acute and obtuse angles, and on into reflex angles done correctly. If you go into a reflex angle, you're going to be talking about a major sector or a major arc as opposed to the minor arc. Minor arcs and minor sectors are predicated, they're based upon the idea of ordinary angle. And ordinary angles, by definition on our course, are angles that are less than 180 degrees and bigger than 0 degrees. Positive angles less than 180. Okay, so they're ordinary angles. So find the area, blah, 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 blah. Here's a circle, so let's represent it on a diagram, 12 centimeters, and we have 2 pi over 3 here. 2 pi over 3, or 120 degrees. Now you might be tempted to say, but I know that's 120 degrees, but to be honest, 2 pi over 3 is better for the calculation. Because the calculation looks so simple when you're getting area, when you have it in radians. It's half r squared theta. Okay, so buy into this. You don't have to convert that out to degrees. You could, and we get the same answer, but buy into the fact that, look, if it's in radians, then the calculation for arc length and for sector area are easier in radians. So we just use the formula that we know from the tables. Okay. So half 12 squared 2 pi over 3. And like I said a minute ago, we'll make that, you know, we'll turn that into one single line, and in our we'll leave out the 1, it's not necessary. We'll put 12 squared times 2 times pi. Look, I can see those 2's cancel, so let me get rid of it. And 3 underneath. So we have 12 squared pi over 3. Okay. Now in the olden days we would have said that's 48 pi. and left it at that because that's how it'll calculate. But if I put pi in, I'll get it, and that would have been in centimeters squared. And that's a correct answer. And I did that with mental maths, but let's do it with the calculator. And we have 12 squared multiplied by pi. 12 squared multiplied by pi over 3. Okay, and of course it's reminding me, yes, it is 48 pi. It's fine, it'll do that. And you can push the ST button. You can also do shift equals to get the approximation digitally directly. And we get 150.79, blah, blah, blah. Don't ever sweat that thing, it's, unless you're in an exam. Don't ever worry too much about the decimal places. And just speed past it and get your answer down. Okay, as long as you know how to do decimal places in the exam, that's all that counts. On to question 5. Okay, so P and Q are points on a circle with center node if the length of the arc is 16 pi. Now we have no idea what the length, what the kind of properties of this arc is yet, as in whether it's acute, obtuse, or reflex. But I have 16 pi there. Well, I do, sorry. And the angle is 240 degrees. Well, let's represent that somewhat realistically then. We're talking about a major sector with 240 degrees here. Okay, and the length of the arc is 16 pi. So find the radius. So now the first thing is it isn't in this simple format. However, you know, I'd really like it to go into that format. Well, no, I'll keep it simple for you and we'll just use the bottom formula. I could convert that into radians and it converts very nicely. It's 60 degrees down here, so it'll be pi plus pi over 6. No, pi plus pi over 3 actually, because it's 60 degrees this way. Should be 4 pi over 3. You could calculate that by going 240 times pi over 180 and 4 over 3 pi. That's fine, but look, we don't have to. We do have a direct formula, so why wouldn't we use it? So the direct formula tells us a way, except the one thing is we will need to rearrange this formula. So you could go, look, and L equals, of course we're doing the exact same thing again that I just did, because all these formulas and that are not independent of each other. They're just all based on the fact that pi in radians is equal to 180 degrees. That connects the top line of formulas to the bottom. So if you use this and the top, then you get the same results. Anyway, so this is interesting how this formula lies, because basically it could be further simplified. It's strange that they don't do that, but they're explaining where it's coming from using the proportion of a full circle. So this could be written from the get-go as pi or theta over 180. But I do prefer that, and that's something you might want to consider adopting. So the length in terms, when you're given the angle in degrees, looks like this. And do we want to rearrange this? Well, not really. The only thing I want to do is say, okay, that's great, but we want OR in this case, so cross multiply up to 180. You get 180L over pi theta. That's equal to R. Okay, so our calculation here was 180 times the radius. I'm trying to get the radius. 180 times the length, which was 16 pi, over pi times the angle in degrees. So the pi's cancel, and we're getting that the radius is equal to 16 times 180 over 240. (16 times 180 over 240), which is equal to 12. Okay, that's question 5. And on to question 6. Okay, so let's get some of these measurements on here. So that's 10 centimeters. And the angle is 5 pi over 8. And we're to find the length of the major arc. So this is actually a very, very simple application of the very first formula, L equals R theta. Okay, because it's in radians. So you have 10 centimeters times 5 pi over 8. Find the length of the major arc. Yeah, that's going to come out fine like this. So that will be 50 pi over 8, 25 pi over 4. Now if we want to know what it's like in centimeters, then we need to actually evaluate that. Pi over 4. So 19.63.